Okay, talk about projections. Let's be more specific. Let's talk about projecting a vector onto a line. Okay, we got a line that I indicate by this fancy script L here, and we got a vector V. To project the vector onto the line, we first draw what we call a projection line. The projection line goes from the tip of the vector to the line. So we take the tip of the vector and we project it down to the line, and it goes down to the line at a perpendicular. So this projection line has to be perpendicular to this line. Okay, this is a projection line. And it's at a right angle. Now, if we know the angle between the vector and the line, let's say that angle is theta, then the projection is a vector from the initial point of this vector out to the point where the projection line meets the line L. Okay, this is called the vector projection. With a vector V on the line L. And we could designate that as projection PROJ subscript L, projection onto the line L of the vector V. Okay, and that's a bad looking parenthesis there. We use absolute value signs for magnitudes, and I'm a little bit used to writing magnitudes, so I started off with a parenthesis, ended up with something like the outside of an absolute value sign. Anyhow, okay, that's projection onto L of V, and it's a vector projection, so we put an arrow over the abbreviation PROJ for projection. Okay. That's simple enough. If we know the angle theta, then we can say the magnitude of the projection is equal to the magnitude of V times the absolute value of the cosine of theta. Remember, theta isn't necessarily an acute angle. We could measure a theta from here around to here. It would have a negative cosine, so we put absolute values around the cosine. Now, if we're doing a vector and a line, then if we make the convention that theta is the closest angle of the vector to the line, then we don't really need the absolute values sign around the cosine. But just to be safe, we want to put that there, and also because of what we're going to do next. Okay. That works, incidentally, if you have a vector. Let's just say you've got a vector here. And the initial point of the vector in this case isn't on the line. I chose to put the initial point of this vector on the line, but let's call this vector W. We can project the initial point of W to the line. We can project the terminal point of W to the line. Again, right angles in both cases. Then the projection goes from the projected initial point to the projected terminal point. So right here is the projection onto L of W. And of course, W makes an angle with the direction of the line. So if we sketch a little segment here, okay, we have an angle here that we could use the same as we did the angle theta here. Well, that's a projection of vector on a line, and we just use very simple trigonometry. You know, the magnitude of the vector is the hypotenuse of the triangle. The vector projection is the adjacent side with the angle theta here, and we just use the fact that the adjacent side is equal to the hypotenuse times the cosine of the angle. Okay, well, now, we can also project a vector onto another vector. So let's just say over here, we've got a vector v, and let's put v, let's make v here. And we've got a vector w. And I don't think I really want to have that direction for the vector w. That angle's too close to a right angle, and that might cause a little confusion. So let me rethink that and put the vector w about here. There's still something I don't like about that, but it's okay. All right, so this is a vector w. To project v onto w, I first think of the line extending as far as we need it through w. Now I've got v and w sitting here with the same initial point. Okay, remember a vector can move any place. So we move the vectors v and w together like this in order to do this projection. Then we, excuse me for blocking everything that I do that, we project v to the line of w. Okay, well, we do that, and again, we end up with the projection. And the projection is going to be just this vector here. And we get the projection again. But we don't call the line L, we just use W. The vector W defines the direction of the line, and the line goes through the root of V because W and V are joined at the root. Okay, the projection onto W of V. And again, the magnitude of that projection is just the magnitude of V times the cosine of theta. So that the magnitude of the projection onto W of the vector V equals the magnitude of V times the magnitude of the cosine of theta, where theta is the angle between V and W. Now there's another connection I'm going to talk about. If we know the components of V and W, it turns out that we can use the product of a row with a column and calculate this without ever having to worry about what theta is. Okay, now remember we said earlier, if you represent, let's say, V as a row and W as a column, then the product of that row and column is the same as what we call the dot product between V and W. So I'm going to talk a little bit about dot product and then use the dot product to efficiently calculate this projection.